Yeah, good morning, everyone. We are on time. Let us continue the topic, the cosmic microwave background radiation, work as the landmark evidence for the history of physics in such a way that how that universe was started, or how that universe was made, how that universe has began, how an accidental discovery is a key to understand the phenomenon of the beginning of the universe actually. That we see that. Yesterday we discussed in such a way that what are all those things actually, what are all the preliminary things which were responsible for that actually. So scientists were doing the experiments on a routine basis, particularly on communications and other part, by making use of certain kind of an antenna. The observations or maybe the hindrance caused made something in such a way to give a solid reasoning or a solid basis for understanding the beginning of the universe. Let us see that how it goes. If that is the case, cosmic microwave background radiation or CMBR they can call actually. What actually it means? According to the Big Bang theory, Big Bang is the theory which gave the very idea of understanding the beginning of the universe. The early universe was a scorching phase. Scorching phase means a place where you can able to identify that what kind of the beginning it was happened of that kind. Almost about 4 lakh years after Big Bang, the Big Bang was thought of having a history of about 13.7 billion years. Sometimes they will also call it as roughly 14 billion years. Billion is about 10 to the power of 9 or about 100 crore years or 1000 million years. 1000 million years. This 4 lakh after 4 lakh years after the Big Bang, and engulfed means and included with a dense soup, hot soup you might have heard actually. Hot soup maybe like water, maybe vegetable or maybe some kind of a soup in such a way that even though it may be in the form of a liquid, but a dense form, a hot dense soup of a hot ionized plasma. Plasma is an another state of the matter, neither liquid state, nor solid state, nor gaseous state. A plasma state is a highly energetic state. It does not belong to the three kind of a matters what we are accustomed to. At this temperature or at this condition of this temperature, electrons and protons would not coalesce into atoms. I don't know whether you got it or not. Yesterday also I was discussing in such a way in a theory class. If the temperature is quite high, how can you keep atoms intact? How can you keep the how can you keep the composition of an atom like an electrons and a nucleons together actually? Electrons, if it receives the energy, gets excited. Sure, if it still receives more energy, it will be ionized. You will get an ionized form of an atoms actually. In the sense, either maybe a positive ion or negative ion. That depends whether the atom is an excess of an electron being a negative ion or maybe a lack of electron being a positive ion. Means to say that the temperatures are quite high. It is a relative technology of the order of millions of degree Kelvin or maybe Celsius, doesn't matter. If you are talking the temperature in terms of millions of degrees, hardly 300 degrees Celsius should differ between the Celsius to the degree Kelvin. As that of that, there is no possibility of the coalescence. You can't keep them together actually. As we know, every object around us, like a table, chair, monitor, pen, paper, piece of paper, even goggles, what you are hearing, what the mobile device you are looking right now, be it the star like sun or a toaster for eating or a metallic rod, which may be at a different temperature, has a thermal spectrum means all objects emits radiation. All objects are known as a black body spectrum of electromagnetic radiation associated with it. Maybe at a black body is the one where the amount of the radiation falling on it must be equal to the radiation which is leaving. Otherwise, the spectrum is in such a way that the thermal coefficient of absorptivity and emissivity it should be equal or ratio should be equal. Whatever it gets absorbed, it emits back to the environment. That is why we can call them as a black body. But if not, maybe for all practical applications, it may look like a black body, but in according to the theory or in terms of the theoretical aspects, all bodies may not be a black body. Some of them will be certainly a gray bodies. All stars are black bodies. Whatever the radiation which got absorbed will be emitted back. For example, Earth, the same amount of radiation may not be emitted back. It it absorbs some kind and it retains some of the energy. It is called the gray body. Gray body means all laws of Wien's displacement law obeys for the perfect black body. If not, for a gray body, it obeys. But thing is that the curve or skewness should be positive. Means it skewness should be towards right of its direction. Similarly, a thermal spectrum of radiation was also associated with the thick plasma, so what we are expecting actually. But as there were no neutral atoms, for example, at that time when the universe was began, these photons of electromagnetic radiation emitted by the super hot plasma, which could not travel very far because which you could not travel very far, mainly because before being bounced back by the electrons. There were also an electrons which are associated. Means if there were no neutral atoms, means there is only an ions and the electrons. Being photons, it should be interacted with the means there is electrons of the photons of the electromagnetic radiation was interacted with the electrons in the environment and bounced back actually. However, as the time went, means as the time went means from 13.5, 13.7 billion years later, the universe underwent a rapid inflation. Inflation means a fluctuations, and due to those fluctuations, universe started expanding. Once the universe started expanding, the temperature started cooling. Means as it goes for an expansion, the plasma within it diluted and cooled down from several million degree Kelvin to layer value eventually. When it cooled below 3000 degree Kelvin, this is an optimum temperature they can call. Neutral atoms finally form at a temperature of 3000 degree Kelvin. Neutral atoms form in the universe, not on Earth, not on solar system, not on a galaxy, Milky Way, where we are living, where we are part of it. Means with no free electrons to redirect the photons at that time, the universe became a transparent for the first time. Earlier, being a dense soup, it was an opaque. Because of the expansion, everything got expanded in such a way, then it became a free. Means I will give you an example in such a way that if there is a fog or maybe a mist, okay, maybe particularly the nearby villages or maybe nearby rural areas, actually, after the sunrise, what will happen? The molecules will absorb the energy, gets dissipated and spread throughout. Once the spreading happens, what will happen? It becomes clear, becomes a transparent. Assume that even a fog exists in a room due to something like that, due to some phenomena of generating actually fog or maybe some kind of a dust or some kind of a mist where it reduces your visibility in terms of an opaqueness. If you open window or if you allow for the ventilation, certainly due to the ventilation, it gets distributed throughout and exhaust will happen and you will see the transparent atmosphere. Means this allowed the photons emitted by hot plasma to now travel way freely. What happens? You see that because of this, right side a diagram is there. That diagram is known as the cosmic microwave background spectrum, which was observed by a spacecraft COBE at that time. At that time means very recently. See the energy, it is the frequency on the x-axis with some intensity like millijoules per steradian they can call. It is a solid angle. From 200 onwards, with the frequency of 1 hour, this frequency is 1 hour centimeter per centimeter they can call, or wave number also can call. This goes up and reaches a maximum value, then it decreases, it becomes slowed down. This graph of the cosmic ray background spectrum is measured by the FIRAS instrument on the COBE satellite. It is the most precisely measured black body spectrum in nature, actually. Okay. Black body spectrum curve looks like blue curve. These dots, red dots, shows the data. What happens? The universe eventually got filled with the radiation. Entire universe is filled with radiation. That is why you may not get the you may not get the signal only from single direction. You will get the signal from the solid sphere. That was simply the remnant heat left over from the Big Bang. What it says is that during the Big Bang of the expansion, due to the expansion, the universe became cooler and cooler and cooler, was reaching some temperature. That minimum temperature, whatever it reached, it started emitting the radiation. That radiation is still we are observing. That radiation is known as the remnant or left out from the Big Bang. Big Bang is known as cosmic background radiation, or and this afterglow of the Big Bang is what we call the cosmic microwave background or the cosmic microwave background radiation. Afterglow is in such a way, if you put a campfire, fire will happen. For example, maybe with charcoal or something like that. If it goes like that, actually, after some time, the fire will switch off, but still heat will be there. Still heat energy will be there in charcoal actually. That left out will emit the radiation, certainly. That left out fire is still hot. That is at lower temperature actually. Basically, similar to that, in CMB also it has happened in such a way that the CMB represents the heat left over from the Big Bang, which has been streaming, which has been continuing through space for the last 14 billion years. Just like the heat from a sun which warmed the rock gets re-radiated at night. What happens during daytime? Atmosphere and Earth receives the energy. Like small mountains or rocky areas are also absorb the energy. Once they absorb the energy, certainly there will be re-emission will be there in the daytime. Once the light is switched off during daytime, means as the sun, as the Earth moves towards nighttime part, still no incoming radiation, but objects like the rocky areas, stones, will still emit the radiation mainly because they really get the energy which is absorbed during the daytime. Being this. Okay, it looks like a statement. There is no way. Now, you might be wondering why it is called the cosmic. The cosmic background radiation is fine. Cosmic rays of either alpha particle, beta particle, or protons, or neutrons, or of elementary particles of that kind. Why it is called microwave? Microwave oven you might have heard. Microwave energy you might have heard. Microwave frequency you might have heard actually. The answer is related to the CMB's energy. The energy which we are receiving is falls within the umbrella of, so falls within the domain of the matter. And that electromagnetic spectrum, if you get starting from gamma rays or maybe the gamma rays to a great extent, gamma rays, then maybe an X-rays, maybe the radiation from the visible, then ultraviolet or infrared, then right away it switch over to the radio waves and the microwaves and the radio waves. Okay. As the universe background light was released billions of years ago, it was as hot and bright as the surface of a star. When the radiation, cosmic background radiation, it was released billions of years ago, we are receiving the same thing billions of years ago. What it was released is we are getting now. Means the radiation which is coming from billions years of ago is the is the significance of is having an information of how the universe was formed at that moment. For example, uh, if we are traveling to a place with 3 days of journey in a train, for example, 3 days of a 3 days of a journey in a train, for example, the dress what you are wearing on the first day, even while getting down or getting out of the train, will also have the same dress, preferably to the extent. Okay. It's of more or less of the same case. For example, if you're coming with some kind of addresses in the morning, you can say that the evening hours is the same case means this is the information what it carried beginning actually. Eventually, the as the universe expanded, the space got stretched actually, stretched out actually by a factor of 1,000. Since then, this centimeter becomes 1 over 1,000 times expansion actually got stretched. Space got stretched in such a way, stretched by a factor of 1,000. Then eventually the wavelength of the CMB photons also got stretched due to a phenomenon called the cosmological redshift. Redshift is the one actually where it can move the energy from higher energy to the lower energy. Due to this expansion of the universe, the CMB radiation has cooled to its present day temperature, which is extremely cold, just 2.725 degrees above absolute zero. Or you can say that 2.725 degree Kelvin, not Celsius. Means absolute zero is in terms of the degree Kelvin. Hardly, slightly, roughly equal to 3 degree Kelvin, starting from million degree Kelvin to about 3 degree Kelvin. Now, if you work out E is equal to KT and E is equal to H nu, that with a temperature of about a 3 degree Kelvin, you work out that energy. That is the energy which is available for background radiation that is coming from cosmos, not from the sun, not from our galaxy, not from our solar system and our sun. It will be from somewhere else. Cosmic background, which is coming from outside solar system, and from outside solar system into the solar system. It is there everywhere. Energy and wavelength corresponding to this temperature lies in the microwave part. You go with E is equal to KT of the electromagnetic spectrum, and so it is the name called microwave background. Although we can't see the cosmic microwave background with our naked eye, I am sure for us, maybe if some of you in your classmates, if you are capable of seeing that, it is a great boon for you. It is present. It is present. It is present everywhere. It is an omnibus, and and it is everywhere in the universe. Whichever with the direction, it is an isotropic, either towards north, south, east, west, up or down, left or right, wherever you go, you'll find the car space. Within house, within department, within building, within hostel, even it will enter in oceanic environment too, to a great extent, depending upon the energy. In fact, if we could see microwaves, the entire sky would appear to glow. Okay, if you are able to see these microwave, if you are capable of doing that, may not be through naked eye, maybe with some devices. For example, we can able to see that the entire sky would appear to glow with a brightness that is uniform in every direction. How it looks? Yeah, this is a beautiful picture. On the left top corner, or you can see the three panels from the left of side. One is on top in 1992, measured by COPE, and second one with the WMAP, another satellite, almost about 10 years interval. Then the last one at the bottom is with the 2013 with the Planck observatory, or maybe observatory is a space observations actually, how the universe looks like. In your entire universe, it is not for the Earth actually. Entire universe is looks like a big elliptical object of that kind. Blue spots are some color, green are of some color. On right side, you can see that this is the latest image obtained from European Space Agency. This is single all sky image captured by the Planck telescope, that is in 2013 later actually, simultaneously captured two snapshots that straddled virtually the entire 13.7 billion year history of the universe. Here the colors are showing that blue is of some kind or red is of some kind. Blue are cooler, red are hotter, sorry, blue are hotter and red are cooler of that kind. I was telling about the electromagnetic spectrum actually. This for example, starting from gamma rays to the radio waves, the wavelength go on increasing, starting from few nanometer to the extent of few meters in terms of frequency. Almost that is, you read this E as the gigahertz, okay? Gigahertz to the petahertz to the of that of megahertz, and photon energy of that of few electron volt, electron volt for the longer wave radiation, particularly micro electron volt, to the extent of kilo electron volt for the gamma rays. We are interested in microwave because, or we are getting the radiation from the cosmic rays, the cosmic background radiation of the order of the wavelength about 1 millimeter to 1 meter. Means few millimeter to about meter. The wavelength ranges from 300 giga for millimeter to 1 meter per megahertz. 300 giga to about 30 megahertz, or 0.3 gigahertz, you can say 0.3 to 300, or in terms of the energy, about 1.2 million electron volt to the micro electron volt of the kind. Being this, what happens? Just think it off. These different colors are in such a way that every 10 years, you are having a betterment of the observations. These colors I will explain later, few slides. See. This is another case. Starting from the Big Bang here, you started way 0 years to the extent of 13.01. This is now 2023 is here. We are going back to the data. In fact, this is the timeline going in a reverse order. you 4 lakh years, 4 lakh years, 4 lakh years from the 13.7 billion years, if you expect actually or maybe about 400 million years as of now, how it has happened. If you go back here actually from the Big Bang, zeroth year actually, see, today is here actually. This is from 0 to the 400,000 years, looks like different color of that kind. If you go for expansion here, this becomes the microwave. This small reddish color is there. No? This is the timeline of them. This pictorial representation, I took it from the NASA of JPL Caltech, Goddard Space Flight Center. They will call it as GSF. So we may not get it from Indian side because the world scientific community works a lot on astronomy, particularly space astronomy at the beginning of the universe. Of course, we are also interested, but we have not gone up to this extent of understanding the phenomena. But we are capable of knowing the science in a better way. We are not we are not second to any one of them. The first one is called the COB, cosmic microwave spectrum. See that somewhere radiation, bluish colors of that kind is the representation of the emission of the energy in a particular temperature. Then still if you go backward, it becomes the dark ages. Here, something like that. The first light has appeared here. This is the beginning. This is the beginning first light about 400 million years ago. A first beginning has happened. If you could have been taken, if you could have been in this, if you could have been captured that image at that time, if you are capable of that time, this is the one kind of speculations they can call actually. With the speculations they made that capture was in infrared, that is in thermal wave band, where the species, the first flight detection was done like this of that kind. Still, if you go, this becomes the visible. See, whatever the night sky you are observing is the same case, visible light, Hubble Deep Telescope or Hubble Space Telescope or Hubble Deep Field Telescope observes, makes the observations actually. This snatch, see that this one, here this one, maybe somewhere this one, this is the one, enlarged one actually. From here to here is the case, what we are expecting actually gives us that how that the sky is looking with different kinds of stars and group of stars and group of stars are called the galaxies. Galaxies of groups are called the universe, entire universe. Being this, let us come back to how that discovery of the cosmic background radiation has happened. Two scientists named Rolfo Alfren first predicted the CMB radiation's existence in 1940. It's the prediction. While he was doing some research related to the Big Bang nucleosynthesis. Big Bang nucleosynthesis, by making use of the Big Bang nucleosynthesis or some experiment, he was trying to extract the information CMB radiations in 1948, almost 65 years. However, practically it was found accidentally for the first time in 1965 when two researchers named Arno Penzias and Robert Wilson, or they can call Penzias and Wilson, associated with the Bell Telephone Laboratories, were trying hard to create a radio receiver. Always you may be remembering in a text, all C programs, all programs earlier to that were done in Bell Laboratories, or maybe like Photon in Bell Laboratories. Didn't critique for Bell Laboratories because that was and is still established laboratory from way back from 8 decades. These two guys were doing research on radio receiver. Radio receiver means, of course, what FM radio you are getting the same thing, or maybe TV stations. Well, when good actually. If as an example of the radio stations, if you switch the FM on and switch over from one station to another, maybe about 93.4 megahertz to about 98 megahertz or 103 megahertz, or maybe if you go back about 80 megahertz of that kind, you will try to hear some kind of a bliss sound. Bzz, something like that. That is the noise created by cosmic background. Or if you are having good enough of having an occasion of a TV, that is a televisions, not from LED make of two versions, a bulk two versions of that kind. If it could have been changed the channel from one channel to another, while or if you are receiving the signal from one group to another group of the signal, you could have been seeing a fainted display, like the bottom of this one, how it is showing it. That is only example I am saying actually here. Something like that, some signals are moving here and there, here and there, here and there, making a noisy of that. And then the signal was fetching. That noisy signal referred to the cosmic background. Cosmic background in microwave frequency, because TV antennas are also tuned for megahertz, megahertz, microwave that kind actually. Means while doing so, Dew was puzzled by an unknown noise that their receiver picking up. Here, what happened actually? These guys were doing some radio receiver experiments, particularly communication thing. Yesterday, I mentioned the same case, but they were observing some noise. Then they cleaned the circuit. They washed the circuit, washed in the sense, they cleaned the entire thing, devices under their part. They cleaned the periphery. This was an antenna. This was a huge antenna of that kind, where the Hallman antenna on which the Penzias and the Wilson discovered the CMB radiation. Okay. Then they thought that some bird might have sitted on the lens, some bird might have sitted on the window, maybe a possibility of some dust. Actually, they wiped out, they cleaned several times, still they were getting the noise. And they were not interested in CNBs. They were not interested in the universe of that kind. They were working on some laboratories, which is some signal processing of that kind. Soon they realized that the noise was coming uniformly. See, if it is coming from one particular direction, like, then you can expect some kind of a source. Means if you are hearing the sound from one particular north, if the train is coming to you from the north, you can say that some object is coming or moving away from that point, like Doppler shift or Doppler effect of that kind. If it is coming from everywhere, all the directions, means you are in the umbrella of, you are in the pitch of, you are in the arena of the radiation environment, or the source of the environment, that should be the ocean of the energy should be there. Soon they realized that the noise was coming uniformly from all over the sky, and was nothing other than the cosmic microwave background radiation that Ralph had earlier postulated. 48 he postulated. Okay, the later in 1950s, Arno Penzias and the Robert Wilson made an effort of identifying that signal, and they got Nobel. That is different story. See that how huge. This is about 5 to 6 feet height actually. Means height, if it goes almost 1, 2, 3, 4, 5, almost about 30 feet height, 35 feet height, width of about almost 100 feet, 100 feet of that kind. This is a rotating machine actually. See that this is encircling like a diameter of that kind. It can receive signal. Nowadays, the antennas are made very well advanced, where they can capture the signal from all the directions. A 32-meter antenna to receive the deep communication at Bailado is one of the greatest achievements for the Indians. What happens here? Simultaneously, a team of researchers led by Robert Dicey in Princeton University tried to find the CMB machine. Within no time, or maybe with a short duration, Dickey's team learned about the Bell experiment and realized the CMB had been found. Had been found actually. Soon after, both the teams published the individual papers in Astrophysical Journal during 1965. Yes, of course, research is like it only. It is not the domain of a single person or of a single country. That is why, as soon as you worked out on some experiment or maybe theory, if you are getting some good results, or if you're getting some good database where it fetches some good information, or it gives the explanation for some of the causes, try to publish them as early as possible. Otherwise, parallelly, any kind of any groups across the world will maybe having findings, and we may not have the climb of ours as the first. That is the one of the reason why India wants to go to moon on the South Pole, and even though we are the fourth country in the world after America, Russia, and China to land on the moon, but we are the first Indians, and ISRO is the first mission, and it made it in a first attempt to land on the southern pole successfully. And unfortunately, and it is the life of the Vikram is coming to an end in a day or two, where the moon is going, our radiation may not reach on the moon. Our people will say that moon is going to sleep from he worked for last 14 days, And as this is the nighttime starts over the moon, the receiver may not receive the solar energy. A dark or nighttime with a temperature of almost about minus 250 degrees Celsius of the order of about roughly 20 Kelvin is the temperature. Or if you want to perform any experiments or measurements at a lower temperature without taking the atmosphere to a lower value, you could have been conducted the experiments on moon now. If they are having a plan with the Vikram, with some of the sensors, that how that sensors work at lower temperatures, starting from zero to sub-zero to about even to extent of minus 200 degrees Celsius, certainly that gives us a beautiful result, but provided the sensors have to work and sensors have to transmit the signals, and that transmitted signal has to reach the receiver on the Earth. In their publications, Vincius and Wilson focused on what they saw, while Dickey's team explained CMB according to what it means in the context of the universe. What happened here? We can see on the right side, 1965, Bell Labs radio astronomers, they called it as radio astronomers, were trying to map signals from the Milky Way while calibrating the horn radio antenna, or you can call it as designated to track the satellite echo. They were interested in the observing the echoes only, okay? Not in the Milky Way galaxy, not in finding the cosmic ray background actually. They detected a constant noise. Constant noise gives us something like that. It is there and it will be there forever in all that direction. This noise was due to the radiation that was the strongest in the microwave region. That is why it's called the microwave background spectrum of the radio spectrum. The radiation was unaffected by the antenna, the sense unaffected by the antenna direction, and was of cosmic origin. It is now called the cosmic microwave background or CMB radiation. Due to their fantastic work in 1978, Penzias and Wilson received a Nobel Prize in physics for their grand discovery. This is the online session is coming to an end in few minutes. I'll stop here. Kindly log in after 10 minutes. Right now, 10:40 in my watch. Log in again by 10:50. I will take about some 25 to 30 minutes. We will complete this discussion. If you're having any doubt, I'm very happy to respond. I'll stop sharing the screen. Stop